All right, so thank you all for coming to Tulsa Tech Fest, especially on the hardware track. I hope you all go and visit our sponsors in the main area. I appreciate you all showing up. This is fantastic. I'm going to be talking about, my name is Jonathan Bartlett, and I'm going to be talking about microcontrollers, specifically geared towards Arduino, but this talk is kind of a general introduction to microcontrollers, what they're used for, and the general process and thinking behind them. The next class in here is going to be going over specifics of electronics, wiring, and programming. So this is kind of the 1,000-foot view, and we'll get into closer detail later. You can you can find bplearning.net has a lot of my books and stuff. I don't have anything on electronics yet. I'm actually working on some of that stuff. Anyway, a little bit about me. Y'all probably don't know me. My primary job is I'm the chief nerd in charge at a company called New Medio, and we do all sorts of things. Our primary bread and butter is probably event registration systems, but we've done a lot of other things too. I'm the co-founder of DocVia, which you might have heard of as IS. They make crash sensors you can mount on your helmet, so it will, if you get into a bike wreck, it'll notify your phone that there's been an accident, and it will send messages to your contact list to make sure you're okay. And so, anyway, I'm the director of the Blythe Institute, which is a nonprofit research and education organization, and then I run BP Learning and BP Books. And you can see some of the books I've worked on. If you are if you are a new programmer, I suggest new programmers start here. I actually built that originally for based on a homeschool class I was teaching. I covered building scalable web applications using the cloud in the cloud session. I think some guy recorded that, so you can actually find that after the fact. Programming from the ground up, I actually wrote like over a decade ago, but it's still in active use. It's on assembly language programming under Linux, and there's the Chinese translation of it over there. It's kind of funny. My actual training is in theology, and so I have this book, Engineering in the Ultimate, which is kind of an integration of science, technology, engineering, philosophy, and theology. And it's based on a conference I organized over at ORU. There's a lot of different places I wonder about online. Some of the main ones, you can find me on GitHub, on Facebook. I write for a homeschool organization called Classical Conversations sometimes. I haven't done that in a while, but I need to get started again. Also, this is new, the Tulsa Open Source Hardware Organization. They used to be an active group. They kind of fell off the map for the last couple of years, but we are restarting it. So if you are interested in this sort of thing, our next meeting, actually our first meeting, is August 24th. It's a Wednesday, and it's in the evening. I don't know exactly what time, but it's at 36 degrees north. I think it's at 6, but you can check their site. It's their space, so I'll go there whenever they say we have time for it. So anyway, so that's Tulsa Open Source Hardware. We're making that available to people of any age, any experience. If you don't know anything and you just want to come and learn, or if you are the greatest hardware hacker ever, come join us. And then I have the forum is still active, and I just have a link to it. It's on Google Groups. So if you go to bplearning.net/TOSH, that'll take you to the Google Groups page. And then I started a Twitter at Hardware Tulsa. So our objectives here is we're going to focus on understanding what microcontrollers are, kind of what the popular ones are, and kind of the different features that you might look for in a microcontroller. Understand what what development boards are and their role in the building process. Become familiar with Arduinos and what they contribute to development. And then finally, a little bit on how you take projects from the prototyping stage to the production stage. Now, I am entirely an amateur on this, so I have very little experience with it, but I know a lot of people who've done it. So as I said, I've been involved with IS, and they had a product that they took to manufacturing. My dad works at a company that makes pumps for the medical industry, and they have development boards, and I've talked to some of their engineers. So I know a little bit about it, but it's not my main thing. I concentrate mostly on education and tinkering. So I do homeschool electronics and homeschool programming courses throughout the year. So anyway, first of all, what is a microcontroller? Okay, so if any of you ever looked at the board of a regular computer, most computers, you've got the processor, and then you've got somewhere else on the board you have memory. Somewhere else on the board you have your I/O controller, and then you have your peripherals. Okay, so the only thing that the chip actually does on a regular computer is it runs your processing. Okay, now on a microcontroller, these are usually single chip computers. So that means that the memory and the I/O controller are actually embedded onto the chip. And then they're also very small. Right? Usually, microcontrollers are usually super teeny tiny. They have a very small footprint. But also, they have direct electronic interfaces. So you can directly control voltages on different outputs. Right? So normally, with a computer, you'd connect to a USB bus. The USB bus would then connect to your device. Here, you're actually doing, hey, I want 5 volts on pin 3. Okay? They're low power. They range from a half a nanoamp to 5 milliamps, and anywhere from 1 to 5 volts. Okay, and you can some of them use a little bit more power, but I mean that's kind of the general range you're looking at. So if you think about a 9-volt battery is usually 400 to 600 milliamp hours. So that's how many milliamps it can sustain for an hour. And so you could run, as we'll see, like a Raspberry Pi runs at about 200 milliamps. So you could probably run that for 2 to 3 hours on a 9-volt. But you could run a microcontroller for a very, very long time off of a 9-volt. They're very low cost. You can go get microcontrollers that are down to 20 cents each. You usually use them for hardware, embedded hardware, where the hardware is separate. Sometimes even there's no network, there's no nothing. It's just the hardware device all on its own. Although there is a new focus on the Internet of Things, where you connect your embedded devices to Wi-Fi, to Bluetooth, to Ethernet, and that's supported on some microcontrollers as well. So now, if you don't know anything about microcontrollers, I thought I'd give you a quick overview of some common microcontrollers. This isn't an exhaustive list because there is a bewildering array of microcontrollers available. So the ones that I focus on because they're used in the Arduino platform are the Atmel AVR series. Okay, and they have most of the ones that are in use are actually 8-bit. They have 32-bit ones, but most of the ones that people talk about are their 8-bit ones. They have between 4K and 256K of flash RAM. Okay, so for those of you not paying attention, that's less than the size of most of my Word documents. So some popular chips, the ATmega 328P is what they stick in most of the regular size Arduinos. Actually, I think I have one here. So let's see here. So that chip right there is the 328P. And then the AT-Tiny only has 8 pins, and it looks like this. Okay, so and then the ATmega 2560 is a lot like the one that they use in use here, except it's got more inputs and outputs. It's got more flash. Okay, another popular one that's used in a lot of devices is the PIC microcontroller. Okay, these are very low cost. They're very inexpensive. They are a little harder to develop for. but a lot of them actually go faster as well. And they're fairly low on the power usage scale. Although one thing that's kind of hard is getting direct answers from manufacturers about how much actual power things consume, because they always want to test in ideal conditions, which aren't necessarily real conditions. And then manufacturers say, well, their chip really isn't that low power. So anyway, specifics are more specific to your application. But the TI MSP430 is another chip that runs in 16 or 32 bits. It's got very low power modes. In fact, that's one of its selling features, that can go into a deep sleep. And I think it says it can be woken up within a microsecond to do processing. So there's the ARM-cortex chip, which is a lot more like a regular processor. It's got lots of onboard facilities as well. And I think it uses a little bit more power. I'm not real familiar with this chip, but it's used in a lot of things that are kind of halfway points between embedded and actual computers. New guy on the scene is the Intel Quark, also the Intel Curie, kind of the same family. And this is a 32-bit Intel processor. It runs a 32 megahertz clock, almost half a meg of RAM. It's got Bluetooth on board. It's got accelerometers, gyroscopes, all sorts of things, and even has what it calls pattern matching technology, but I'm not sure how exciting that is. Sometimes advertisements give you more excitement than what's really there. And there's actually been very few people who've actually put these into production, so there's not a lot of information about them. Then there's older microcontrollers. The 68HC11 was a very popular one at one point. Usually programmed that in assembly language. An old one that they used to use for a lot of education is the parallax stamp, and that's because it actually had a BASIC interpreter on it. So you actually did microcontrollers using BASIC, which never made sense to me, but you know, to each their own. Then there's the Intel 8051. And this is kind of one of the chips that really made microcontrollers really made headway in the microcontroller space. It's no longer manufactured by Intel, but pretty much every microcontroller company has a variant of the 8051. So as I said, there's a whole lot of different things. Now, one thing that is not really a microcontroller, but sometimes gets lumped into it, is the Raspberry Pi. And I would call a Raspberry Pi, rather than a microcontroller, a very small computer that also has direct hardware interfaces. Because I was looking online, and it pulls about 200 milliamps at 12 volts. So that's, I think that's almost half a watt of energy. So that's not something you can really run off of a battery very well for very long. So we talked about, so those are the basic families of microcontrollers that you might find around. But then you have what's called the development board, okay? And the development board accomplishes a certain number of standard tasks. Well, their main goal is to make prototyping circuits easier. Development boards, they usually provide power supplies, right? Because one of the things, I don't know how much electronics experience you all have, but one of the biggest issues with any electronics project is reliably delivering power. Because, for example, even if you supply something from a 9-volt battery, you're not necessarily getting 9 volts all the time. And so providing reliable power is always a problem. And so a development board has the power regulation pre-built into it. A lot of them have programming interfaces to make it easier to reprogram your chips. They have, these are called headers, these little black things along here, that make it easy for you to plug things into. Some of them have hardware clocks. A lot of the microcontrollers have internal clocks as well, but you can run them even faster if you have an external clock. They can also have other integrated hardware. The Arduino has an integrated USB port, and then a convenient packaging for testing things out. Okay, so that's what a development board does. It basically gets you jump started for making making prototype circuits. You wouldn't ever take a development board. You would rarely take a development board and use it in production. But if you just wanted to try out an idea, it has all the basics done for you, and you just have to do the things that you're interested in. Okay. So that takes us to Arduinos. An Arduino is an open source microcontroller development suite. Okay, it's a whole conglomeration of tools. Okay, it consists of, first of all, an Atmel AVR microcontroller. We're looking at those. That's the Tiny. That's the 328P. A couple others. You can actually use a few other processors as well, but that's what it's focused on. A microcontroller bootloader that enables it to pull programs out from USB. Okay, so this thing has a USB controller in here, and then this chip has a bootloader installed. So when it turns on, it checks the USB to see if there's a new program waiting for it. So that makes it real easy. You know, some of the older boards you had to do incantations and dance a certain way to get it to get stuff onto the board. But this makes it really easy to get stuff onto your board. It's got both open source hardware and software. So the Arduino IDE is open source, and the board layouts are open source. And then there's also the Arduino branding that they have. And so this is kind of, when someone talks about Arduino, this is what they mean, this whole suite of things. Okay, because you can do AVR microcontroller programming without the IDE. You can do it without the development board. And so all of them together is what makes up Arduino. And so this is the standard Arduino board. So as I said, a lot of what your programming or your electronics projects are is power regulation. So this whole section right here is power regulation for the Arduino. This chip manages the USB interface. Okay. This is actually a full microcontroller itself, because managing USB is somewhat of a complex task. So it actually has a full microcontroller dedicated to it. Here is the clock crystal, so it makes sure you can get a consistent clock. As I said, I don't know if this particular chip does, but most Atmel chips have internal clocks. If you don't have, it does. Okay.
It's normally set to like 1 megahertz, but I think it's set to 10.
Gotcha. So, and you can get up to 16, and some of them, I think some of them you can do up to 32 with the external clock. And then it has rows of pins. These are used for digital I/O. These are for analog I/O, and these are for power. Okay. Because it actually has multiple. This thing can feed power from multiple different ways. If I have this plugged into USB, it'll actually feed power from my USB port. If I don't have it plugged into USB, I can plug it into the wall with this DC jack. If I've got a DC power supply somewhere, I can do a DC jack, and I think that takes 7 to 12 volts. So pretty much any DC plug you have around that.
You can even just plug it in a 9-volt battery.
Yes. And then you can also plug it, if you just have wires, you can plug it in to this VN. Will take pretty much any power, 7 to 12 volts. So that is the Uno. There's a lot of other standard Arduino configurations. This one is the Mega. Notice it's got a lot more I/O pins. This is the Nano, and I have a Nano here. So very small, and this has almost all of the features of the regular Arduino. And so it's got instead of a full-size USB, it uses micro USB. So it's pretty much identical in development. You have Arduino Pro, and one of the reasons why it's called a Pro, it doesn't have any pins on it, it doesn't have a USB on it. You're responsible for all that stuff. But if you need something that's small, lightweight, you already have all the management stuff. This is an easy way to get that integrated into your projects. And this is an interesting one. The Arduino 101 actually uses the Intel Curie chip. So they actually switched. You can do Arduino development, the same development tools. You just select the board, and even though this is a completely different processor, your tool chain will take care of it. So there's Arduino clones. Okay, there's a lot of sellers will sell Arduino compatible clones. Nothing against them. I actually sell them myself. If you buy the full Arduino from Radio Shack, they cost $35. I sell clones that do exactly the same thing for $10. The only difference is that the USB controller is usually different on the clones because you can get the clones use a much cheaper chip, and you have to download another driver. That's really the only difference. So to use a clone on Windows or Mac, you have to install the driver first, but after that it's just like normal. And if you have Linux, Linux already has the driver. So and they're exactly like it. If you cared, here's how you tell the difference. First of all, the genuine Arduinos will have the official Arduino logo, and the fake ones usually just have kind of a generic logo, or they may have a different logo altogether. There's a few of them. They used to have some people who sold clones using the official logo, but I think most places have started not doing that anymore, because I think eBay and Amazon were able to shut them down so that only the official ones use the logo. The other thing you can tell is by this chip right here. And if it says Atmel or FTDI on it, it's probably an official one. If it says CH340, it's probably a clone. So anyway, you can get a lot of add-ons for Arduino. There's a lot of things that come in packages that are easy to use. You can get them, first of all, you can get standalone devices. So like for example, this is a Bluetooth chip. So if I want to connect my Arduino to Bluetooth, I just use this guy, and I stick him in the board. And like magic, if I know the programming, then I can get him connected to, get my Arduino connected to Bluetooth. But even easier, and I don't really do this, but some people like it, there's a lot of things that are called shields. And what they are, and I don't have one to show you because, as I said, I don't really use them, but they're basically, they take a board and you just slide them on top of here. So you don't have to plug them into a breadboard or anything. You just put the shield directly on top of the Arduino, and it will use the pins it wants to use, and then let you use the rest of the pins. And so you can kind of stack these on top of each other and add different types of functionality just by sticking these things together. It's nice in theory, but you have to be sure that the boards are made to play nice with each other, because if they both use the same pins, it doesn't work. So there's a lot of things that I prefer just the straight up sensor modules, because I think you have to learn that stuff anyway, so you might as well just do it. But it is kind of nice if you just wanted to stack some stuff together, you didn't want to wire anything up. It's a little bit more convenient. So as I said, there's also the development environment. The Arduino development environment is very nice to use. It's written in Java, so it runs on Windows, Mac, and Linux. And it's fairly straightforward to use. So it's got a simplified programming environment for microcontrollers. That's one of the biggest issues with microcontroller development, is just teaching people how to get started. And so Arduino has taken all the getting started part away. You can just go and start programming. Okay. So you don't have to know how to initialize the chip right. You don't have to know any of that. Arduino will take care of that for you. You just program it. Okay. It uses C++, which C++ is in its simplified usage. It's very easy to use, but C++ is one of those languages that can easily get away from you if you let it. But most of the programs on Arduino are fairly simple. Use a fairly simple subset of C++. There's a library framework for handling board functions. So like there's a library for almost anything you could add to it. So you don't, if you want to directly program it, you can, or like this works as a serial device. Has anyone in here messed with like modems back in the day? Yeah. So some of you people have. So this works just like a modem. All right, it's got an AT command set and everything. but basically it's got 2 pins, one for transmit and one for receive, and it would be hard to directly wire those pins. So instead, there's a serial library in Arduino that you can use to manage that communication. So Arduino takes away all of the build load issues for microcontroller development. It automatically pulls in the libraries you need. It automatically does all the linking and anything with make files or anything like that. It handles all the uploading for you. It even automatically switches tool chains if you're programming for a different processor. Okay, so if I switch this guy out with another Arduino compatible processor, I go from the AVR to ARM-cortex. I just have to select it, and all of a sudden I'm building with a different chipset. So anyway, it's got a manager that lets you pull in libraries easily and pull in boards easily. The general Arduino development process is simple. You write the program, you click the compile button, you plug your Arduino into your USB port, you click upload, and it'll save the software onto your chip. And so that literally flashes, this has flash memory on it, it flashes the chip with your program. From that point on, this thing just has to be plugged into power in some way, and it's got your program stored on it. So just to show you what a simple program looks like, this is the Blink program. And the Blink, for those of you not familiar with devices, Blink is kind of the hello world for device programming. If you can turn a pin on and turn a pin off, then you kind of know how it works. Arduino code is set up into 2 sections. There's a setup section and a run section. And in setup, you basically, the biggest thing that you do in setup is you tell which of your pins you're using for input and which of your pins you're using for output. And so this is going to blink whatever's on pin 13. So it says pin mode, pin 13, output. So that sets up pin 13 to be an output to be an output pin. So that means if I go in here, so let me turn this guy on. There we go. Where do you turn the light on? Light?
It might actually be on the light. Oh, no.
There we go. All right. So you can tell these pins are all numbered. And so 0 through 13. So we set pin mode 13 to output. So that says this pin is going to be used for output. Okay, so we can connect an LED to it or something. Go back to my. All right. So setup runs once when the board boots up. After it's booted, it runs the loop function over and over and over again for as long as there's power. Okay. And so what this does, what the blink function does, is all it does is it digital write. So I'm writing out to pin 13, and I'm setting it to high. And your digital pins only have 2 states. They can either be high, that means we have voltage on them, or they can be low, which means we have 0 voltage on them. Okay, so we write 13 to high. So that turns whatever's connected to it, which is, for blink, you're usually connecting an LED, turns the LED on, delay 1,000. So for 1,000 milliseconds, 1 second, I'm going to leave that guy on. Then I'm going to digital write 13 low. Turn it off. Wait 1 second. Okay, so what happens at the end? We're done with the function. Well, what this does, it loops it over and over again throughout the entire time the device is on. So it'll keep on doing this over and over and over and over again forever. Okay. So now Arduino has a few drawbacks. It's not C++ is not the most user-friendly language, but I think it's one thing I like about Arduino is that it's like if you think about the Lego Mindstorms and things like that, those are interesting platforms, but they don't lead someone closer to knowing more about about robotics and electronics, right? So if you teach someone how to do Lego Mindstorm programming, that doesn't get them a lot further along doing other things. So C++ I think is good because it's simpler than microcontrollers, and it leads you a little bit closer to knowing how the harder stuff works. The other thing, and we'll get at this more in the next course, but it doesn't really have an event model. It just runs that loop over and over again. So it makes a lot of programs difficult because you have to yourself program for, like if I push a button, right, we normally think about pushing a button as just doing something. But actually when you push the button, physically, the button has a little bounce and wiggle on it. Okay, so when I push a button, it actually kind of hits that button about 5 times when I'm actually pushing a button. And so you can accidentally, depending on how you write your program, if you don't account for that, one button push might be registered as 5 of them. Okay, so that's now, as I said, in the next course we'll talk about how to handle that, some specifics on Arduino programming that we can use to make that easier. Also, the Arduino environment doesn't encapsulate some important chip features, right? So you can set these chips in very low power modes. So like you can have them sleep for, if you want something to sleep for an hour and then take a measurement of something, all right? Well, the chips are capable of having very, very, very low power sleeps, but the Arduino environment doesn't give you any access to that. So it's possible to do it, but it's not nice and pretty like the rest of Arduino is. When we turned the pin on, we just did digital write 13 high. When you turn it off, it's digital write 13 low. There's nothing equally simple for saying go into a low power sleep. So, and I'm kind of, you can write something for it. There's probably libraries for it, but just by default, there's some important chip features that are missing from the environment. Also, Arduino does not have very many good debugging features. You can print out kind of program state through the USB port, but there's not like, you can't step through a program like you can if you compile it locally. And there's chips that are capable of doing it, but the Arduino environment doesn't support it. So, as I said, Arduinos are mostly used, and development boards in general are mostly used just for prototyping, because you wouldn't, if you're actually going to deliver something, you probably need a different form factor. You might need it smaller. You might need it to do something else. You might be coming from a different kind of power source. Another thing is that the Arduino operates at 5 volts. These chips can also operate at 3 volts. So if you wanted to operate at 3 volts rather than 5, you need your own power regulation. So so once you have a prototype, you don't have a final product, but you're on your way to having a final product. So if you remember that view of the board that we saw, most of the board was focused on power regulation and USB communication. That's most of what that board does. And so without those features, pretty much all you have is just the chip itself. So once you have your Arduino doing what you want it to do, the first step is to get it to do it without the board. So you make it look something like this. So this is the chip. This is the same chip that's in the Arduino. It's just outside of the board. Okay. Here we put it on a breadboard. But and so there's just a couple of pieces that need to be inserted, but you can get a pretty minimal configuration. It doesn't need any of those things that we use for development. The things that we use for fast development, we can get rid of. And then, if you have an ATT Tiny, which is this guy, he requires even fewer pieces. He basically only needs a voltage source, a ground connection, and that's actually it. And then whatever input-output pins you want to have connected. So just 2 pins. Voltage, negative, and whatever pin you want connected. That's it. So you can do. So what you would do is you'd build it on your Arduino, you get it working the way you want it, and then you'd flash your program on one of these, and then rebuild your project on a breadboard like this with just the chip. Okay, so that's kind of a phase 2. And then once you have that working, you kind of think about, okay, well, how much space do I want this to take up in the final build? Is this something that's a big device, or is it something that needs to be super tiny? Figure out what form factor size you need. You also need to figure out how much power consumption you need it to take. Is this something we're going to plug into a wall? Is it going to run off of a coin battery? Can I have a big laptop-sized battery? What are my power requirements? How long do I want to have it functioning? How long do I want to have it functioning away from power? Other things like that. And then finally is cost. How much do you want to spend on the components? Is this something that's going to retail for $10? Is it something that's going to retail for $1,000? All these affect how much work you have to do to get something to work, and what sort of components you're going to need. So I kind of outlined here kind of the basic steps you would do to take something from an Arduino to production. So first thing we do is we build a working prototype using a standard Arduino board so the functionality works the way we want it to. Okay? So then the second thing is we rebuild that same chip. Once we have it working the way we want it to, we rebuild that same project on a solderless breadboard like this. And we'll talk more about solderless breadboards in the next session. And get the chips working by themselves so that we have an accurate list of all the components we need. Because if we have it on an Arduino board, I can't tell you the final list of components that we're going to need to manufacture it, because there's a lot of stuff on there that we don't need. And so what I need to do is just get it down to what parts do I need, and how do I get them to work together. And so if I have it all laid out on a breadboard, I can just go and look at each piece and figure out which pieces I need. So then you need to measure how much current you're pulling from your power source. And once you know that, then you can figure out, hey, am I using too much power? Does it work? Does it not work? And if you're pulling too much power, you say, well, how can I redesign this so that it pulls less power? And that could be putting the chip to sleep. It could be some of your other circuitry is pulling power. And you just test all those different, test each wire, see how much current is going into each wire. And we'll talk in the next section on how to limit current and things like that. So let's see here. And so and also on the AT Mega chips, you can actually turn off certain chip features even while it's running, not just sleeping. You can turn off certain features. It's got a brownout detection feature. So it can keep running even when there's a little lower voltage on it. And you can turn those things off because those things consume power on an ongoing basis. And then once you have a prototype that meets all your specifications, what you need to do is you need to create a board layout. Figure out, how do I want this stuff laid out on a physical breadboard? Okay, so I have a list of components. How do I want it laid out? And there's a lot of tools that can use to help you with it. There's a tool called fritzing, which is a great tool that helps you. It gives you 3 different design views. It gives you a schematic view, a breadboard view, and then a physical board view. So you can have the same circuit in all 3 views. So basically, you use the schematic view to design it from your mind, and then you use the breadboard to figure out how you want to actually lay it out on the breadboard. And once you verify that it works, then you use the breadboard, the regular breadboard tool to actually figure out where you want the wire traces in production. So then, and one thing to keep in mind on that sort of thing is that the size of components and the spacing of components matters. Different manufacturers have different abilities with how far the spacing they can use, and so you just need to. Those are the kinds of things you need to keep in mind when you're doing this sort of process. Finally, you develop packaging to hold your board for the project, and you find a fab facility to build it. Right? We don't have these machines cost way more money than any of us probably make, so we don't have these in our backyards. We have to find a facility to build our boards. And then the other thing is you need to test your boards and make adjustments. So they've got people who make these like 10 at a time, so you can get like get 10 boards, get them back, test them out, see if they work the way you want them to. Also, when you mass produce, it's also important to provide a testing environment. Just like in code, you have unit tests. You actually have the same thing in electronics production. You'll have what's called test points, and you have different places on the circuit that you can have them test automatically for different voltages to make sure that all the components were laid out the right way. So I've got two case studies in here. First one is the iStock crash sensor, and that is this guy. All right. It's one of the first devices to use Bluetooth Low Energy, which gave two really important features. First of all, it gives you a very long battery life. The other thing is that it's much easier integration with iOS. Anyone who's done iOS development, they are actually very strict on what hardware you can connect to, or at least they used to be. I don't know if they still are. But Bluetooth Low Energy was the first thing that allowed any peripheral to connect to iOS, and so that was a big deal. So let me show you what this thing looks like. So all right, so that is the device, and so what you have is this is basically TI put out a bunch of development boards called Connect Blue. Okay, and what iStock did is they basically took the Connect Blue boards and just it had almost all the features they needed on it, because this has a gyroscope, an accelerometer, a Bluetooth connection, and a microcontroller. That's basically what's on, and a battery charger. All right, that's basically what's on here. And so what they did is they basically took the development board that TI produced, and they built kind of a test version with that. And then for production, they just relayed out the board in the way that matched the form factor they wanted. And I think they also upgraded the gyroscope and the accelerometer to more sensitive devices. So basically, you use the development board to prototype, right? And that gets you a long way towards what you want, but you still have to lay out the final components in the way that you want it. And you might say, hey, they gave us kind of a junky accelerometer. Let's give it a better one. So the whole chip is, so under the shield has the chip that handles both the Bluetooth and the actual processor. The processor is 8051 based. Remember I said that everyone has an 8051 processor. That's what's in here. And it's fabricated by a company called Flextronics. All right? So that's the. So if you buy a iStock crash sensor, that's what's inside. And then the other case study is Compression Solutions. They do pumps for the medical industry, and so this is their pump control board. And so remember, I said most of what's on a board deals with power regulation. All right, so this whole area is the power regulation part of their board. Okay, so basically what it uses a PIC microcontroller here, power regulation, and then it connects to the actual pump. So this turns the pumps on and off and different switches. And so then those physical components connect to these different sockets. And so basically this powers the board, this controls the logic, and then one thing that happens a lot is that your microcontrollers don't have a lot of, they can't push out a lot of electricity. Okay, they fry after about 20 to 40 milliamps, trying to push out that much power. So what you do if you need to drive something bigger than that, you use these guys. And these guys will take small outputs from the processor, combine it with what you've got here, and will turn on and off other things over here with higher power requirements. All right, so almost this whole board actually deals with power requirements. You've got the logic chip here, you've got input and output, and then power requirements. So that's a lot of what goes into making a board work. Let's see here. So the nice thing about using a microcontroller, like you can think, well, they could probably hardwire a lot of that logic in, right? But one of the nice things about having microcontrollers is you can reprogram the logic when you need to. Also, when you don't have things that are hardwired together, like here this actually had more connections, but they wanted to prototype something that had fewer, and they physically just cut them off the board and gave themselves a smaller form factor. And because they weren't physically connected, they were only logically connected, it didn't affect the circuitry. And then another thing that they're working on is they're working on a call home feature. So they're going to add in another little device that has a GSM unit on it. And actually, it's really cool. You can actually get GSM accounts for devices for $2 a month. So if you want to have a device that connects to the cellular network, you can connect through Twilio, and they'll connect you for, I think it's $2 a month, and then 10 cents a meg. So it's for low bandwidth uses, but anyway, it's got a. Oh, sorry. So and then when I was talking to their engineers, they just let me know that one of their biggest issues is finding good part sourcing and fabrication facilities. Sometimes you can find sensors that you might want in units, and then you're like, well, I can't figure out how they got that. I can't find an individual sensor for that low of a price, and so trying to find the sensors you want at the price you want them is sometimes hard. Like for example, just in my own stuff, they have sensors that can detect bend in a wire or in anything. Those sensors cost like $10 each. That's more than the whole Arduino costs. So anyway, so part sourcing is an issue, and then fabrication facilities. Finding a good fab facility is important, and designing your board in a way that the fab facility likes it. There's trade-offs between the form factor and ease of manufacturing. As I said, when we try to shrink it down too much, your wire traces are smaller, your pins are closer together, and it takes more and more expensive equipment to run it. And then also, if you ever work with offshore manufacturing, you have to be very specific about all your needs, because you can't assume that they're going to include something in the process just because you think they are. So anyway, questions? Yes?
What that crash sensor was, I was just trying to look it up, I can't find it. Or do we just get directly through you?
The crash sensor?
Yeah.
Oh, the crash sensor is the IS-dot crash sensor.
IS-dot.
Yes. Yeah, I don't sell them at all. I helped them start the company, but most of my input is on the application side. There's a phone application that goes with it, and most of my development was on that side of it.
Is that a local company?
Yes. Yeah. Other questions? How many of you here have actually done anything with Arduinos? Good amount. How many of you are completely new to the whole microcontroller area? A few of you too. Excellent. So as I said, we're starting the Tulsa Open Source Hardware meetup, and it's going to be at 36 Degrees North, which if you don't know where that is, it's I think it's 1 or 2 blocks. I don't know the street name. It's 1 or 2 blocks to the north of Archer. What?
It's corner
Cameron and Maine. So anyway, that's happening on August 24th. It's a Wednesday, and it starts either at 6 or 7. You'll have to look at the calendar. And if you go to bplearning.net/TOSH, I have a link to the mailing list that you can sign up for, and I'll be sure to get better information out there. So.
I was